All right, let's start straight away by reviewing the highlights of yesterday's lecture. Okay, highlights might be person dependent, but let me recap what we need in the first part of today's lecture. We started to look at the tree-level amplitude prescription in the RNS formalism. I wrote down the worldsheet action for you and at least gave you an account on the meta part in this conformal field theory. There were the worldsheet scalars, xm, and the worldsheet spinors, psi and psi bar. They all carry a space-time index m, running from 0 to 9, but from the worldsheet point of view, these space-time indices are just spectators and don't really worry us in our CFT calculations. Okay, and from what you saw, the meta part of the worldsheet action is quadratic in the fields, which means that in computing correlation functions, all you need to know is the two-point function, and then you can upgrade it to n-point functions by using the Wick theorem and doing some combinatorial exercises. There's one disclaimer that I should have made yesterday. The claim that the n-point functions are trivialized by Wick rules, this only applies in the Neveu-Schwarz sector when you scatter space-time bosons. Because if you want to generate a space-time fermion in the RNS formalism, you come across the subtle ingredients, including the spin field. And okay, it is still true that lower point functions determine all the higher point functions, as usual in CFT, but in presence of a spin field, things get slightly more complicated than just mindlessly applying Wick rules. It's a solvable problem, but it's not sufficient to refer to Wick rules in that case. But okay, we'll only do the space-time fermions in pure spinor, so this is nothing that will bother us right here in the lecture. Just approach me if you want to know more details. Okay, so within the comfort zone of the Wick rules, let's take the two-point functions that you saw yesterday and just put them together to compute the n-point correlation functions underlying the worldsheet integrand of space-time boson scattering. One particular way of composing the bosonic two-point function is the Kober-Nielsen factor. It will appear over and over again in probably every lecture of this week, so please recall that shorthand here. And then, when coming to the vertex operators of the massless bosons, I told you that you need two representatives of the same physical states, two superghost pictures for one and the same gluonic state. You will see in a minute how you should distribute these two choices. But there was one unsatisfactory part in the discussion yesterday. I did a bad job connecting with the buzzword superconformal primary. I was telling you that these two different representatives of the gluon field that they are related by a superconformal transformation, but I failed to give you a reference. So I looked it up. If you want to see the details on why the two are forming a doublet called superconformal primary, please open section 12.1 in a nice textbook on string theory. It's the textbook by Blumenhagen and there are many nice textbooks on the market, but this is the one where I happen to know the section. Okay. Yeah, so if you want to know the reason for my claim that these guys form a superconformal primary, please consult this section. And of course, that statement about superconformal primary is meant to be modulo the ghost field here. Yeah, so this concludes the recap from yesterday. Unless there is a question on this right now, I will tell you how to put these things together to compute tree-level amplitudes. All right, so this will be section 2.4. That's the tree-level amplitude prescription for open strings. I'll ask the fans of the closed string for a little bit of patience. We'll do this tomorrow or on Thursday, recycling our open string knowledge. And To make life even more simple, let's focus on one particular color ordering. Let's only stare at the coefficient of a particular trace ordering for the color degrees of freedom of the external states. So we'll be interested in an object which was denoted as follows in yesterday's lecture. We look at the color-ordered open string amplitudes for n massless external states, and this is meant to be a cyclic function of the scattering data of leg 1, leg 2, and so on. So you can do cyclic moves within this labeling to reflect the cyclicity of the accompanying trace. Okay, and as you already saw yesterday, this cyclic ordering in the trace and in the color-ordered amplitude, it refers to how you arrange your vertex operators on the boundary of the disk. And my favorite parametrization of the disk boundary is the real axis. So once we have committed to this cyclic ordering, we should better impose the following inequalities on the integration variables on the disk boundary. Okay, so if I make changes here, I need to revise the integration domain. Now, the integrand, in turn, is going to be a correlation function that does not care about the ordering. So everything I'm about to do here should be permutation symmetric. And a formal way of manifesting this permutation symmetry in the integration measure, I write this formal expression here. So this will be defined in a minute. Okay, and the heart of the integrand is a correlation function of vertex operators. So all of these things refer to the guys you saw, you're seeing right here. And maybe some of you got nervous about getting two vertex operators. Which ones do you want to use in the amplitude calculation? And it turns out you need to go for a hybrid choice. You need to use some of the -1s and some of the zero picture vertex operators. And the only constraint on the admissible choices is that the ghost charges, denoted by Q here, should add up to -2. Okay, so this is a tree-level formula, and it might look a bit unsatisfactory. Why the hell is it ghost charge -2? The reason for this, it has to do with counting the number of fermionic moduli that you can fix at genus 0. And if you do this counting of fermionic moduli more carefully and more generally, you will arrive at the conclusion that if you were to do two G-loops, then the sum of the ghost charges should better be 2G -2, which at tree level becomes -2. Yeah, so you need to adjust the composition rules for the vertex operators to the genus at which you are working. But maybe you're still nervous. I just told you that the overall ghost charge should be -2. But there are many ways to make these ghost charges add up to this number. How to decide which ones of the vertex operators to put in the -1 picture. And here is a very bold claim. It is far from obvious from what I discussed so far. This formula here, with total ghost picture -2, is actually independent on how you distribute the charges. So, in other words, the claim is you can set these ghost pictures to be -1 for any two external states. Okay, sorry for the many, many subscripts. Here, the subscript of the Q, you can choose it, so for any two states, I and J, you can put them into the -1 ghost picture, and otherwise, you take the zero picture for n minus 2 states. Okay. Yeah, as I said, this is far from obvious from what you have seen so far, and it requires more subtle ingredients related to the beta-gamma system. But changing a choice of these Qs, yeah, it amounts to BRST trivial moves on the worldsheet. Okay, but this is not the end of the rope of the choices we can make here. I should tell you something more about this inverse volume of SL2R. Of course, it's utterly formal to talk of the volume of SL2R because it's infinite, but dividing it out means you avoid an infinite overcount. Let me say this in more practical terms. So formally, when I instruct you to divide by the volume of SL2R, what I really mean is that you should drop some integrations. You should drop integrations over 3 of the punctures, and once more, you're completely free to choose which ones of them. It's the same kind of luxury which was around for the choice of super ghost pictures. And even better than that, the choice to be made here is completely uncorrelated to the choice there. You can choose ABC completely independently on how you decided to proceed here with the super ghost charges. Okay, but dividing out or skipping the integrations is not the end of the game. You must also insert something in the numerator that compensates for your choice of A, B, and C. So you need to put here the absolute values of the respective differences into the numerator. So you will see in an example in a minute why this is actually necessary to avoid the integrand from blowing up if you fix a puncture to infinity. Now, where this thing comes from, you can, for instance, view it as a kind of a Jacobian in changing variables from the n punctures to the coordinates of the respective moduli space, which is only n minus 3 dimensional. So there's a change of variables from n punctures to n minus 3 degrees of freedom in the moduli space. Okay, so the job of this fixing is to freeze the freedom to do Möbius transformations of the type z goes to alpha z plus beta divided by gamma z plus delta. And you can really derive from this transformation that this is the right kind of Jacobian. So when I'm not sure about this, I go back to the 3-point function and demand that it changes sign if I change 1 to 3 against 3 to 1. But this is a very result-oriented way of proceeding. Yeah. Okay, so I'm firstly telling you can skip these 3 integrations. And once you skip them, you must, of course, make a choice for these punctures. And a particularly convenient choice, for sure not the only one, is that you send any 3 punctures to 0, 1, and infinity. So just to be clear, this is a recommendation for your convenience, but it's by no means compulsory. Convenience to choose these 3 fellows and to choose these points to fix them. Okay, so the first suggestion to think about the numerator is being a Jacobian. A second way how you can think about them is as a ghost correlator. You can get this as a 3-point correlation function of the C-ghost field, which I shamefully neglected in the discussion up to now. So you can get this as a 3-point function of a conformal weight minus 1 field. And if I want to incorporate this into the opening line, it means that I must formally adjoin a C-ghost to any triplet of vertex operators. That for any triplet of vertex operators, you replace the V that you have been given by the corresponding C-ghost at the same position times the vertex operator. Namely, for those external legs, ABC as above. Okay. Yeah, so this might make you feel a bit lost when there are so many choices around. Let me make sure that there's at least one consistent choice on the blackboard. That's also the one that I'll be using in the subsequent examples. A possible choice to deal with this cornucopia of freedom is you can make this prescription collapse on the following. You will see it in the examples. I want to get the 3-point Young-Mills vertex without any decorating factors in alpha prime. And likewise, the field theory limit of the 4-point function should not have any alpha primes in it. It's just an artifact of the conventions here, nothing deep. Okay, so I was promising you a possible choice. So as I already confessed, this is how I like to fix the punctures. And for the ghost pictures, I'll now send the first n minus 2 of them into the 0 picture. And I place the last 2 in the -1 picture. Okay, so we want to use 0, 1, and infinity for the locations of the fixed vertices, but when you look at the expressions for CFT correlators, then you might worry, is it okay to put one of the punctures to infinity? So let's check whether there is an issue with sending one puncture to infinity. Let's not send it to infinity on the spot, but let's first contemplate whether this limit is finite. Okay, so here I was giving you the Jacobian that you need to insert to compensate for the choice of fixing. And when you insert 0 and 1, then the only thing that really contributes is an absolute value Zn square from up here. One of the ZABs will be 1, and, well, the other 2 will essentially go like Z infinity. Okay, so here we have 2 infinities in the numerator. Is the correlator strong enough to compensate for this growth? And the good news, it will work because that vertex operator is a conformal primary of conformal weight 1. So if you just open up early chapters in CFT textbooks, they will tell you about conformal primaries that their fall off at infinity goes like the conformal weight to the power -2. Yeah, so having this conformal primary of weight 1 in the correlator, it automatically implies that the correlator in the second line has a fall off, Zn to the -2 at infinity. So to summarize, this limit, Zn to infinity, is perfectly okay, because the correlator in the second line will go to 0 with this fall-off rate, and the Jacobian here makes sure that you get something finite in the limit, Zn to infinity. Yeah. Are we all fine with the spurious infinities? Okay, and the last thing I should comment on, once you have done this fixing, then the remaining integrals are all happening in the unit interval. So the conditions here in that SL2 frame translate into these inequalities. And okay, this might again be a personal choice or preference, but I like it to have my punctures in a finite-looking interval between 0 and 1, because this is pretty close to the world of polylogarithms and multiple zeta values. You'll see the benefits in one of the later lectures of this week. Yeah, so this is the story for endpoints. Are there any questions before I proceed to a 3-point example of that? All right, so next one is a 3-point application of this general prescription. And before applying the formula, let's first of all contemplate about the momentum phase space. What I mean by phase space is how many degrees of freedom are there in the kinematic variables if all external states are massless and if we have 3-particle momentum conservation. How many Lorenz scalars can you form with vectors subject to these conditions? So at 3 points, the answer is pretty disappointing. All the Mandelstams are 0 in the 3-particle phase space. So in other words, the Kober-Nielsen factor, which will be definitely part of all of these correlation functions, the Kober-Nielsen factor is trivial. This Kober-Nielsen factor just becomes 1. That's why you won't see it when we go through the example step by step. But just because the exponentials give you a trivial Kober-Nielsen factor, it doesn't mean that they don't contribute in intermediate steps. The exponentials are still ready to contract against the dx field in the vertex operator in the 0 picture. So this is elaborated here on that blackboard. So here I'm evaluating the 3-point function in the SL2 frame, with a choice of superghost pictures that I recommended to you. For sure, all of these vertex operators have a polarization vector that I'm pulling out of everything. Here is that Jacobian, or the C-ghost. Here are the superghosts, so this is just an inverse factor of Z to 3. And okay, so this is probably the most challenging part to deal with the conformal weight 1 fields in the 0 picture vertex operator. I gave you a general formula, or no, not general, but I gave you a example of a correlator involving those guys. You're contracting them against the exponentials. And when the dust settles, this exponential contraction should land you here. But in order to check that this really happens, you need to exploit that if you contract epsilon 1 with K2, this is minus epsilon 1.K3. So this uses both momentum conservation and transversality. I can highly recommend to go through this calculation in detail by yourself, and this will allow you to appreciate the transversality constraint, because without it, you wouldn't get a dropout of the z-dependence. Yeah, one of the surprises in going from the second line to the third line is you don't see any z's whatsoever. So this is reflecting the fact that we do a 3-point function of conformal primaries of weight 1 after adjoining the superghost contribution. So please check for yourself that there's really no z-dependence here. And there was a question before on whether or not to put an absolute value in this Jacobian / C-ghost correlator. I wish I had a first principle answer to the question, but what you want is that you get a minus sign when changing the 1 to 3 to 3 to 1. And since the correlator in the second line does not carry absolute values, this is the only way out that I see. But maybe there is a first principle explanation of the absolute value.
If you did the computation with the operator formalism, you get the total sign.
Okay, so you agree that the net result is having an absolute value?
No.
Oh, you don't? Oops. Okay, so more invariantly, the color structure of the result should be the FABC of the gauge group and not the symmetrized three trace. Okay. You mean the story with the infinite overcounting? Or? Ah, okay, okay. Ah, okay, okay. You mean complex momenta? Okay. Okay, yeah, I agree. If you're really honest and say plug in 40 Spinor helicity wave functions, then indeed it's strictly speaking zero unless you go to complex momenta. Since I didn't commit where the momenta are exactly living, I didn't really plan to talk about that aspect, but yeah, you're right. There's a catch for real momenta. Okay. Yeah, what else? This term over here is just coming from the psi term, and this is easier to evaluate. There is no transversality constraint in action. Right, you have to add this trace, and also there is another term with 1 to 3 relabeled to 3 to 1. And you want to get the differences of the traces to produce the FABCs of the gauge group. Yes. Okay, is there anything else I wanted to add? By the way, if you were to do the same calculation in the bosonic string, you would get an additional alpha prime correction. So let's notice that the answer is homogeneous in alpha prime, namely independent. But for the bosonic string, you would not only get this Young-Mills vertex here, but on top of that, you would get a higher order alpha prime term, which signals an F-cube interaction. So here, using the superstring vertex operators, we have verified that there's no F-cube in the superstring. How could it be? It's not supersymmetrizable. All right. Are there any further questions on the 3-point example? If not, I will proceed to 4 points. It's probably most instructive if you go through the intermediate steps yourself. You will notice that if you don't use this, you will have trouble canceling out the z's. For both the bosonic string. It's only getting worse in the bosonic string. Yes?
You get a leftover. If you don't use that, you can always put in that form, but you get a leftover. And okay. Just to say, if you take that amplitude of shell, you get what is called, you compare with the field theory, you get the so-called German ball gauge.
Oh. I see. Okay, let's do 4 points. Again, starting with a brief discussion of the momentum phase space. Let's again use momentum conservation and the masslessness condition. And here we do have some non-trivial Mandelstam dependence, but only 2 out of 6 Mandelstam variables are independent. Why do I say 2 out of 6? With 4 particles, there are 6 pairs how you can put 2 of the momenta on the Sij variable. And of course, by momentum conservation, many of them are directly equal. And where you have to work a little bit harder is the S13 and S24 to express those guys in terms of S12 and S23. Okay, so here in total these should be 4 relations for 6 Mandelstams, leaving you with 2 independent ones. For instance, S12 and S23. And with these relations, we can bring the Kober-Nielsen factor in the following pleasant form. Oh yeah, to make it really pleasant, let's already implement SL2 fixing. Let's go to the frame with Z1, Z3, Z4 at 0, 1, and infinity. And then on the right-hand side, you only see two Mandelstam variables, namely two which are independent under these relations here. Okay, I did a bad job in keeping the surprise alive. You already saw the spoiler in front of your eyes all the time. To make sure that I'm not making any sloppy mistakes, I have already spelled out the opening line for the 4-point function, again in a particular choice of ghost assignments. And this mysterious subscript here means that I'm only tracking one tensor structure. Namely, only the tensor structure where the epsilons, the polarization vectors, contract each other in this manner. I mean, you already saw it at 3 points. There will be several tensor structures in the answer, and I guess it would keep us busy all week if we were to do everything at 4-point right now. So I will only evaluate those terms for you which are carrying this tensor structure. And I use this shorthand. Okay? So let's not evaluate the entire thing, but let's take a look from the distance which terms in that correlator, which pattern of Wick contraction rules are compatible with this tensor structure. I don't want to contract an epsilon with a k, so I won't be contracting the dx against the exponentials. But instead, in order to arrive at this tensor structure, we want to make sure that these guys contract if they are both around. And likewise, for the psi's, this fellow wants to contract that fellow. And furthermore, to get the epsilon 3, epsilon 4, let's make sure that here, those psi's also contract each other. Okay, so this is the small subset of the 4-point correlator that I will evaluate for you now. And we go to the usual SL2 frame, which is indicated over there, to make sure we can use the nice result for the Covariant factor. Yeah, so this smells pretty much like the integral which we have seen yesterday in the opening example. Yeah, so as I was saying, this guy here is from the SL2 fixed 4-point Covariant. Then let's see, what do the contractions here give us? Well, Z4 is infinite in that frame. And you heard a general argument before why all the Z4s will compensate each other. You can check it for yourself if you like. But you have my word that the infinities disappear. So let's look at the conformal fields at finite positions, Z1 and Z2. In this contraction, you produce a double pole, 1 over Z2 square. And the inverse alpha prime here is engineered such that you get a compensating 2 alpha prime from the 2-point contraction. Okay, but then there's also a term with the psi's. There are more alpha primes floating around, and if you do things carefully, this fermionic term is off by 2 alpha prime k1 dot k2. And if you go through all the Wick contractions of the fermions, you will find another double pole. So this is from the term that has the maximum number of psi's, which is a total of 6 according to my counting. All right, in the best case scenario, this is the moment to compare against yesterday's claim that you can factor out a 4-point Yang-Mills tree and that the leftover integral is the beta function at nice arguments. I think we are almost there, but there's one subtle intermediate step, namely the Covariant integral that you saw yesterday in my claim for the 4-point function was of slightly different type. I gave you yesterday a Kober-Nielsen integral which had a single pole in Z2 and not the double pole from up here. Now, the resolution to this is, in order to get from double pole to single pole, there's a rational function in alpha prime that mediates between the two. You can track this by using the gamma function representation, for instance. And when the dust settles, you will find that by shifting the arguments of the gamma function, you effectively replace the 1 minus S12 by this one. So what happens in between the lines, I have converted the double pole integrand to a simple pole integrand. And of course, this is only valid under the integral sign. So either you check this by going through the gamma function representation, or you can also show that it's integration by parts, discarding some boundary terms that take you from here to there. Okay, so this is on the nose yesterday's integral, which we were calling Z4 point yesterday. And let's not forget, we are looking at a very specific tensor structure. So in comparing with yesterday's claim, we should also check how does this tensor structure here appear in the Young-Mills amplitude. And if you carefully track what is the coefficient of this tensor structure in the Young-Mills amplitude, you will find that this S12 becomes an S23. Okay, a lot of intermediate steps that are a starting point to encourage doing the calculation yourself in one of the afternoons, evenings, or later weeks. Just get in touch with me if you have questions on the intermediate steps. Okay, so this is meant to give you a lightning consistency check that this RNS tree-level amplitude prescription is consistent with yesterday's claim that the overall 4-point function is the Young-Mills tree times that Kober-Nielsen integral up here. And you have seen yesterday what kind of physics is contained in that Kober-Nielsen integral. There's one kind of moral that I want to take home from this discussion. Suppose you look at this double pole integral and you evaluate its poles using the procedure yesterday. You will find that per se, this double pole integral would have a tachyon pole. So there's something fine-tuned happening here. This numerator, 1 minus S12, is tailored such that it cancels the tentative tachyon pole. So in changing variables to this integral here, I've chosen an integral which is manifestly free of tachyon poles. As you saw it yesterday, this integral doesn't have the tachyon pole. So the moral that I want to convey here, that worldsheet supersymmetry is your friend. How did we arrive at this 1 minus S12 factor? It was the interplay of the d-axis and the psi-psi's in the zero picture vertex operators. If you go through the intermediate steps yourself, you will find that only by the cooperation of these two fields, you build up that numerator on the double pole. And having this numerator is crucial to avoid that the overall amplitude does not have any tachyon pole. Yeah, so worldsheet supersymmetry cancels the tachyon. You've heard this a zillion times, I believe, but this is a concrete manifestation of that at the level of the 4-point amplitude. Okay, I admit this was really a fast-paced walk through this calculation and only tracking a specific tensor structure, but I chose this tensor structure deliberately to show you this effect of how worldsheet supersymmetry avoids the tachyon pole. Yeah, so this would conclude the introduction to tree amplitudes in RNS. I would now proceed to pure spinors, unless there's any further question on this. Oops.
I mean, the reason that there is no detachment is that the detachment is not produced in the operator algebra of the zero class sector.
Absolutely, yeah. So operator algebra.
Symmetry by itself doesn't keep the vacuum. It's just the GSO projection that keeps the vacuum.
Okay, I like the buzzword operator algebra. I mean, you can just look at the zero-picture vertex operators in empty space. If you look at the OPE between them, they will have a double pole.
Yeah.
However, the double pole will be accompanied by the compensating numerator. So this will have okay, so this is an invitation to do integration by parts. And of course there's some simple pole stuff with more on the numerator. But if you are careful, if you also take the contribution to the Kober-Nielsen factor along, you will find that this, together with that, and in particular the numerator, that all of this really calls for integration by parts as early as possible. All right, you'll shortly see the pure spinor version of this. Yeah, before starting with the worldsheet action, let me make a few opening remarks that you might have already heard yesterday or in other places. One of the major motivations to do the pure spinor formalism is to manifest the space-time supersymmetry. So in the RNS formalism, there was only a worldsheet supersymmetry manifest relating the dx with the psi. But okay, so this is just a model that we use in intermediate steps of the calculation, and this doesn't manifest the SUSY in space-time. So in pure spinors, in turn, the worldsheet variables will have a different index structure in space-time. So instead of introducing a worldsheet spinor, we will have a space-time spinor in the CFT, where the spinor indices refer to an irreducible of SO10. This will be a Weil spinor of the 10-dimensional Lorenz group. Okay, one of the advantages of using space-time spinors is you don't have to deal with the subtleties of Neveu-Schwarz and Ramond sectors for the psi of RNS. So, among other things, the psi in RNS forced you to introduce so-called spin fields to describe space-time fermions. And even worse, if you want to look at Ramond-Ramond sector states, you have bilinears in spin fields. Well, you didn't see a spin field in the worldsheet action yesterday, and in fact, I'm not aware of a good way of incorporating spin fields into a worldsheet action. That's why RNS might not be the optimal starting point to address Ramond-Ramond backgrounds. But for pure spinors, there are no spin fields. And therefore, the pure spinor formalism is often advertised as a much better starting point to address Ramond-Ramond backgrounds. So with the final goal of computing string amplitudes, for instance, in ADS5 times S5, the pure spinor formalism guarantees that certain inconveniences related to the spin field won't hit you. There are other manifestly supersymmetric formalisms which are more qualified for Ramond-Ramond background, so for the moment I'm only comparing RNS with pure spinor. There's, for instance, the hybrid formalism, which could be useful for RR backgrounds in lower dimensions. Okay, but this lecture is mostly about flat space amplitude calculations, and in this discipline, the pure spinor formalism is leading in the following sense. The pure Spinor framework was the first instance that a three-loop calculation could be carried out. More specifically, it is the low energy limit of the 4-graviton amplitude at 3 loops that has been evaluated using pure spinors. And this has been done by Carlos Mafra, who probably will show up later today, and Humberto Gomez in this legendary paper. And they should be correct because their result agrees with the prediction from S-duality of Green and Van Hove. So one of the motivations for the project was to check the S-duality induced prediction. Yeah, so this is a calculation that has never been done with RNS so far. I'm curious to see how it would look like. And also at tree level, I will show you a result for the endpoint function for massless trees. And in principle, everything has been around in the RNS framework to do that calculation, but it was based on the pure Spinor approach that this calculation has firstly been completed. So this was done in 1106 by myself and Carlos Mafra and Stefan Stieberger in this doublet of papers. Strictly speaking, this three-loop calculation has been done by a so-called non-minimal modification of the pure Spinor formalism. There exists the so-called minimal and the so-called non-minimal pure Spinor formalism. For the moment, you will see the minimal one, but if I get there, I will later this week comment on the non-minimal pure Spinor formalism, which has more variables than you will see today. These are the opening remarks. Let's now get to the worldsheet action of this model, of the minimal pure Spinor formalism. This time I will be more explicit about the ghosts, but before introducing the ghost sector, let me first give an account of the meta variable. And the meta part of the game has already been largely accomplished in the 80s by Warren Siegel. Warren Siegel found a nice modification to the more traditional Green-Schwarz worldsheet action. Well, I didn't really talk about the Green-Schwarz formalism, but it is one of the traditional approaches that has been around from the early 80s on. Also, Green-Schwarz manifests spacetime SUSY, but it's very difficult to quantize it in a Lorenz covariant manner. One usually goes to the light cone to do Green-Schwarz. But in pure spinors, there won't be any need to do light cones, as you will see. Yeah, and Siegel was interested to find a modification of Green-Schwarz. And he got pretty close to what is now the minimal pure Spinor formalism. He got the meta sector right, though he did not yet know about the ghosts. Yeah, so the meta sector he got is, well, this guy is identical to the RNS. And then he adjoined some variables, P alpha and theta alpha, that are spacetime spinors. I was telling you before, whenever you see an alpha, it's a Spinor index, ranging from 1 to 16, Majorana Weil. Majorana Weil of SO, ranging from 1 to 16. Absolutely, this is the next bullet point. So these funny hatted variables are meant to take the right movers into account. I will largely ignore right movers, but the only remark I can't help making here is that there are two choices here. The chirality of the hatted and unhatted alpha can be chosen in two different ways. Either it's the same chirality of Weil spinors, or it's the opposite. Of course, the same issue arises in RNS if I had spelled out the spin field. So depending on whether you want to have the same or the opposite chirality, you get different theories. The same chirality will take you to the type B theory, which has two scalars in the 10-dimensional spectrum, and the other choice will take you to the type 2A theory, with only the dilaton among the scalars. Okay, one other comment. In this section, I start to be lazy and not track the alpha primes. So it's a matter of dimensional analysis to reinstate the inverse alpha prime that is hidden here. Yeah, given that there are now space-time spinners around, you can be sure that you meet plenty of gamma matrices. So let me spell out the conventions used in this lecture and in most of the pure spinor literature. Oh yeah, right, it's a first-order system indeed, and the conformal weights are 0 and 1 for those two variables. In the Green-Schwarz formalism, the analog of P alpha is constrained. And one of the big deals of sequence modification was to interpret P alpha as being an independent dynamical field. So in the next formula, you will see plenty of gamma matrices, and more precisely, I will use the chiral blocks of the gamma matrices, or 16 by 16 Pauli matrices, with one vector index and two Spinor indices in the usual manner as you know it for Pauli matrices. And in 10 dimensions, the single gamma matrix is symmetric in its Spinor indices. And for the experts of representation theory, I'm strictly speaking looking at a product of gamma with a charge conjugation matrix. But don't worry about that. Let's just say they are symmetric in the Spinor indices. And the possibly more defining property is the Clifford algebra. If you look at the anticommutator, in both chirality configurations, the anticommutator always gives you a Kronecker. A Kronecker in the Spinor indices, so it's just the unit matrix, and a Minkowski metric for the spacetime indices. So just the old school Clifford algebra. Then we will often see antisymmetric products of gamma matrices, the Clebsch-Gordan coefficients for the polyforms. So the conventions for the antisymmetrized gamma products is such that if you totally antisymmetrize in the Lorenz indices, then let's adjoin a factor of 1 over r factorial, counting the number of terms in this antisymmetrization. Yeah, and this will be denoted just with a single parental letter gamma and a collection of Lorenz indices upstairs. And for some of these antisymmetrized products, there are symmetry properties in the Spinor indices. So the 3 form is antisymmetric, and the 5 form is again symmetric. So these are some lemmata that will occasionally be important, will occasionally show up in the later calculations. Good. So even though I have introduced the fundamental fields to be del x and p alpha, it turns out that some changes of variables will be convenient in later steps. Namely, for the purpose of spacetime supersymmetry, it would be good to use worldsheet variables that are invariant under spacetime SUSY. I've not given you the charge for spacetime SUSY, but believe me, if you want to have supersymmetric quantities, you should do some redefinitions. Some redefinitions which render the pi and the alpha variables spacetime supersymmetric. namely the dx field. You should shift it by a half theta gamma partial theta, and p alpha wants to be shifted by minus a half plus a quarter Okay, it's mostly causing you work of writing, but if you look at the corrections, it's nothing scary. It's just some expression built from the variables you see upstairs in the action. Okay, so these are the variables I will prominently use in the following. And I started RNS by giving you the OPEs. So now for pure Spinor purposes, I will directly give you the OPEs of the good variables, which respect space-time SUSY. So in the worldsheet meta sector, there are 4 OPEs that you need to know about. So pi is essentially the dx field. And you have seen the dx OPE in the RNS section. And the shifts from dx to pi, they don't really disturb you in evaluating the double pole. So you can reinstate a 2 alpha prime here if you like. Okay, then what might be slightly more interesting is the space-time spinors, where you haven't seen the RNS analog. So d alpha is mostly p alpha plus corrections. And p alpha in turn appeared as the conjugate momentum to the theta variable. Oh, sure, yeah. Right, I'm sorry, that should have been specified what I mean by the tilde. Suppressing regular terms. So already the z to the power 0 terms are suppressed in stating these OPEs. Yeah. Exactly. Theta doesn't have OPEs with theta, exactly. And also del x doesn't talk to theta. Exactly. All right. So where was I? Yeah, this is probably easy to understand. If it was a p alpha, it's directly obvious from the OPEs. So the leftover work is to check that the shift here doesn't screw up the OPE. Okay, so here's one example of an OPE where the shift from p alpha to d alpha is important. Namely, this OPE for the p alphas would be 0, but now that we have the SUSY completion, there is a non-vanishing residue. Namely, it's a gamma matrix times the pi variable. We will use this in a second to check nilpotency of the BRST charge. And finally, this mixed OPE, the d alpha with the pi field. Again, this is something which you wouldn't get with a p alpha and del x. This has another simple pole with residue del theta. So is it clear what I mean with this one? There is a bispinor gamma, and there's a upstairs spinor indices here, but I don't write out the contracted spinor index. Okay, so all very nice up to here. This is that Siegel modification from the 80s. And why didn't we start computing space-time supersymmetric amplitudes back then? This model has a problem with a central charge. I told you yesterday that in RNS, the critical dimension allows you to get vanishing central charge when combining matter and ghost sector. And here, as it stands, we just have matter fields. And by adding up their contribution to the central charge, you get plus 10 from the dx, minus 32 from the p theta system, which gives you a total of minus 22. And adding a BC beta gamma system won't help you here. So this is currently a problem. In absence of further worldsheet fields, we have a conformal anomaly. So that's a place where we need to work on. And this is where the pure spinor ghost will come to our help. Adding a ghost sector. So you can already anticipate we need a fine-tuned ghost sector which manages to cancel this choice of minus 22 central charge. Okay, and let me start with a spoiler. The right ghost sector, to fix it, has the following action. Okay, it's not yet the full spoiler, but we are close to it. Take the matter action up there, and let's add a pair of ghost fields called W and lambda, both of which carry a spinor index. And there's again the story with left and right movers where you need to make a choice for the relative chirality. Okay, I'm already introducing these variables as ghosts. As you know, ghosts have opposite statistics than the index structure gives rise to expect. So if it's spacetime spinor, then being a ghost means that they have Bose statistics. Both W and lambda. Okay, so one of the central requirements on that ghost sector is to make the central charge disappear. So by adding the central charge minus 22 with the central charge of the ghost system, you want to get 0. Okay, so if you just play with this kind of first order system, you would conclude the central charge is proportional to the number of components. More precisely, it's central charge plus 2 per component. But if it was an unconstrained Weil spinor, the 16 components would certainly not give you minus 22. 22 is not divisible by 16. However, minus 22 is divisible by 11. So wouldn't it be nice if W and lambda were to have 11 components? Okay, so this might sound a bit esoteric to you at first glance, but there is a very beautiful construction to constrain a spinor, a Weil spinor of SO10, to have 11 components instead of 16. So the magical trick to attain these 11 degrees of freedom is to impose the so-called pure spinor constraint. So this is now the definition of what a pure spinor is. A Weil spinor of SO10 is defined to be pure if this quadratic relation holds. If you sandwich one of these Pauli matrices in between two lambdas, you want to get 0. So just to be clear, this is a vector-valued equation, and it is imposed to hold for each value of m. So we want to keep the description Lorenz covariant. So for every choice of the vector index, this should better vanish. And you might naively think these are 10 equations, so shouldn't this kill 10 components? But if you do a careful analysis, using, for instance, a U5 decomposition of that guy, you will find that only 5 out of the 10 components are independent constraints. A very careful account on this can be found in the thesis of Carlos Mafra. Oops. It's an archive with February 2009. Oh, shame on me, I don't have the last numbers, but just look for the papers on archive of Carlos Mafra, and you will identify one of the papers from this month as his thesis. And this is where you can read more about why there are 5 independent constraints. Okay, so good news. With this choice of ghost system, by adding a pure spinor and its conjugate momentum, we get the right central charge. Oh yeah, I didn't mention the implication on the W variable, the conjugate momentum. Now that lambda is a pure spinor, there's a gauge freedom to W. You can shift W by something like lambda gamma m. So also for W, the pure spinor constraint ultimately kills 5 physical degrees of freedom, because 5 of them are pure gauge now. Okay, let me now come to some more fine-tuned consistency checks on this model. The central charge is fine. The next thing we want to have from our model, it should be equivalent to the RNS formalism for amplitude calculations. And one of the key engine of amplitude calculations are the OPEs. And a very specific OPE that I want to check with you, it concerns the Lorenz currents. So in the RNS formalism, the psi that you saw in the zero picture vertex operator is in fact the Lorenz current. And we want to make sure that the Lorenz current in the pure spinor formalism gives you the same OPE. Okay, and this is another place where ghost and meta variables will conspire in a delicate way. Given that the ghost sector is formed with spacetime spinors, they will contribute to the Lorenz current. So this bilinear here is normalized in a way that it has the usual OPEs of Lorenz currents. Let me spell them out. So first of all, if you OPE the Lorenz current with the pure spinor, you get a simple pole. More precisely, there is some gamma matrix decoration upstairs. And if you OPE the Lorenz current, which is with itself, so this is the OPE I want to put more focus on. You want to realize the Lorenz algebra here. So let's just go to a textbook on Kac-Moody algebras. If you OPE the currents for some Kac-Moody algebra, you want to get a simple pole with more currents in the numerator. Strictly speaking, with the structure constants of that Kac-Moody algebra. Okay, so this is just following the standard law on Kac-Moody currents for SO10. And now, Kac-Moody currents, or representations of Kac-Moody algebras, are labeled by a so-called level. No worries if you haven't heard what a level is so far, but let me highlight. If you use the pure spinor ghost system, then there is some meaning to the coefficient of the double pole. And there is a -3 next to okay, so this number -3 is the so-called level if you line it up with the literature on Kac-Moody algebras. It signals that we have level -2 for the ghost contribution. But in RNS, if you look at the analogous OPE with psi, for sure you won't produce a number 3. This might sound pedantic, but I would like to insist that the overall Lorenz current should have the same level, the same double pole coefficient as in RNS. Okay, so far this was just a discussion of the ghost sector. Of course, the overall Lorenz current will have contributions from both ghost and matter. Let's combine those, and the overall Lorenz currents are the ends from upstairs, and then matter contributes some term involving p and theta. This is the Lorenz current of the matter sector. Okay, so if you do the analysis for the OPE in the matter sector, what you find is the level is additive. If we make a sum of Lorenz currents, the overall level is the sum of the level here and this level there. Oh, okay, I'm some sort of suppressing this one. This is splitting into angular and orbital part, right? So I'm only tracking the orbital part. Absolutely. There's also the angular part, which is identical in pure spin on RNS. It's, as you say, x and dx anti-symmetrized. Yes. Okay, so the total level, as I said, is additive. From the ghosts, you get a minus 3. And now, for the matter, I mean, you have seen the OPEs, and you just go ahead and compute the coefficient. It's plus 4. So, in other words, the total level is plus 1. And this turns out to be a reason to celebrate. This is the level we get in RNS. The level of the current algebra generated by the RNS fields. Okay, so in other words, the matter and ghost sector in pure spinor are fine-tuned, such as to reproduce the Lorenz current OPEs of the RNS sector by taking ghost and matter together. You will later on see how they appear in the vertex operators. With which variables? Oh, okay. I have to remind myself, it's far from straightforward. Yeah. I think a expert on this is Marcus. I guess we should have a chat, the three of us, to set up a more detailed dictionary. Okay, so there are good indications that matter and ghosts are nicely combined with the above pure spinor action. Let me go on with a further observation on how matter and ghosts are tuned. This overall action has a global fermionic symmetry. Exchanging ghost and matter variables. And instead of writing down the symmetry transformations, let me give you its generator instead. Namely, there's a charge given by this contour integral of lambda alpha d alpha. So this is the ghost, the pure spinor ghost. This is the conformal weight 1 field from the matter sector. And the claim is, if you hit all the fields in the worldsheet action with this operator, you find that it generates a symmetry. And you can hear that I'm really careful with the wording. A symmetry that combines matter and ghost, well, we usually know this under the name BRST operator. But usually, we derive BRST operators by gauge fixing a slightly more symmetric action. So here, the history in the pure spinor formalism is quite funny. Initially, this Q was just postulated to take the role of the BRST operator. So maybe I should have given this reference earlier on. The birth of the pure spinor formalism is this paper here of Nathan Berkowitz. And yeah, he was presenting this as a tentative BRST operator, but he couldn't derive it by gauge fixing a more symmetric action. Instead, he had overwhelming evidence that it's a good choice, but not yet a derivation. But Nathan kept on thinking about this, and later on, he found a procedure to derive this to be a BRST charge from gauge fixing a more symmetric action. So this is how we usually arrive at BRST operators. He also had a paper in 2014 on that, but according to Nathan, this is the more valuable reference on that topic. Okay, I won't go with you through the derivation of this from this gauge fixing, but instead, let's do one check in front of your eyes. It should better be nilpotent if it wants to be a BRST operator. So in order to compute Q square, you need to evaluate the OPE of this fellow with itself. Okay, there are no OPEs between lambda and lambda, but for the D field, you see the OPE upstairs. D alpha with D beta will have some non-zero OPE. So what you will get is, from the d alpha, d beta OPE, you generate a pi field. Okay, and both the d alphas are multiplied by a pure spinor. So you will find that the coefficient of this pi field is given by lambda gamma lambda. But hang on, by the pure spinor constraint, this is 0. So in other words, this candidate BRST operator is nilpotent only if lambda satisfies the pure spinor constraint. So this is a second reason to really like the pure spinor constraint. Not only does it give us the right balance of central charge and Lorenz currents, but on top of that, it ensures that the BRST charge is nilpotent and really allows for a cohomology. Yeah, so this is some good validation for Q. We will apply it to construct the spectrum in a minute, or maybe, let's say, shortly. Let me just give you one useful formula before. When you act on some superfields, we will shortly construct vertex operators in superspace made of the x and theta variables. Using the OPEs that are hidden on the other blackboard, you'll find that on superfields, the BRST operator acts through the covariant derivative d alpha. So this is quite similar to the four-dimensional incarnation of the covariant derivative that you may know from Wesenberger and elsewhere. It's almost a theta derivative, but on top there is this extra term involving the x derivative. Okay, and as a consequence of this definition, these covariant derivatives have a non-vanishing anticommutator. They anticommute to the momentum. All right. So the next step is to construct the cohomology of the BRST operator to obtain the spectrum. At least at the massless level we will do that. And this will be a useful lemma in evaluating the intermediate steps of the job of finding the spectrum. So it's 10 minutes to 1. Is it okay if I do another 15 minutes? Okay. Good. I'm aware I'm the only thing between you and your lunch, so try to be brief.
So what do you mean by superfield? That it just depends on plane waves, or you can have...
Oh yeah, right.
I mean, on the worksheet.
Okay, here I have been careful. I have not yet committed to how the superfield will depend on x. But later on, we will assume a plane wave ansatz, and then you can replace it by the momentum. But at this point, it's not necessary. You just use, you just do the OPEs using the Leibniz rule and the chain rule.
So S of x of theta can be any function of x?
Any function of x and theta. Yeah, exactly. The only assumptions are there's no dependence on the Worldsheet derivatives. There's no del x and no del theta.
There is no del x.
No del x. Sorry, this I should have spelled out. Okay, so let me try my best to keep the promise. In the RNS case, we saw that by checking out for the spectrum, we found transverse polarization vectors. And this, in turn, was the signal that we are describing Young-Mills. Now here, I want to do the analogous thing. I want to find out the BRST cohomology as the massless level and identify it as a field theory. And to make sure that we land on a field theory you know, I want to introduce 10-dimensional super Young-Mills now. And this superspace description I'll be giving is largely based on an 86 paper of Witten. So the starting point of this description of 10-dimensional super Young-Mills will be some UN-valued connection which is very similar to what you know from Maxwell Electrodynamics. The opening line to derive Maxwell or to describe Maxwell Electrodynamics could be that you introduce some connections like that. But now the idea is to do this in a supersymmetric manner, adapted to the 10-dimensional superspace, or more precisely, 10 is the number of space-time dimensions, but the superspace of interest has another 16 theta coordinates. So this is the chiral superspace, off-shell superspace for 10 dimensions. So the idea is to define a connection not only for the bosonic directions, for the x coordinates, but also an analogous connection for the fermionic directions. So in the simplest case, you would just take the theta derivative, but for a reason you see shortly, we are better off to insert the covariant derivative right here. Okay, and so now these fields, AM, I want to be able to get Born-Infeld. Later on, these amplitudes will be computing contain in the abelian limit Born-Infeld.
Because I was thinking string theory gives both UN and S prime.
Yes, yes.
As a spray
Okay, I thought let's be less restrictive here. Are you worried if we keep it with UN, or do you fear? Yeah. Okay. Okay.
The curiosity is the following.
Okay.
Is construction limited to UN, or does it work also for SON?
For SON, for the orthogonal. Oh, okay, okay.
But this is a subgroup of UN, right? You just truncate the states that that's...
Not always easy, so easy.
Okay.
If you have no commute with the theory, it doesn't work.
Okay. Okay, I didn't think about that. I think nothing in the next 10 minutes would change if I replace UN by some generically algebra G. Okay. So these are the actors. Let me now put a theory on shell. And it turns out with these connections, there's a very slick way to put the theory on shell. We just need minimal input, namely Bianchi identities or Jacobi identities, and we need to impose one equation. We want that the anticommutator of these fermionic connections closes to be the bosonic connection. Now you can probably see why I wanted to mention this property of the d alphas on the previous blackboard. So if you wish, this is a nonlinear extension of a property which the theta covariant derivative has anyway. So what's happening here is we are about to define a field theory, and we put it on shell by imposing this and exploiting Bianchi identities for nested commutators. So this very minimal input is enough to derive meaningful equations of motion that will, at the end of the day, leave us with 8 + 8 degrees of freedom. Let me elaborate on that. By Bianchi and this manually imposed condition, we arrive at the following nonlinear equations of motion. Namely, for each of the connections, we want to have a statement on their fermionic covariant derivatives. We want to have something to say for each d alpha. So the constraint we started with, if you plug in the definition of the connection, you can easily verify that you get this stuff here. It's just sorting the d alphas and the superfields. And yeah, you generate the vector superfield by starting from d alpha on the spinor. And as I said, we want to make sure we always have a satisfactory answer for d alpha on each of those fields. Now, if you go on hitting the vector with a d alpha, then you first of all go back to the spinor with a space-time derivative, but also you will generate a field that we haven't talked about so far, W alpha. So let me note the definitions on the other blackboard. This is a gauge covariant field strength. So here, this is quite similar to Maxwell Electrodynamics. The commutators of covariant derivatives are covariant. So this is what you know from Maxwell, the curl with respect to two space-time directions. But also, you could look at a curl with respect to a mixture of directions, a bosonic and a fermionic direction. And this is the definition of this W field. But there's also a non-trivial content to this equation. We are looking at a vector spinor, which by general Lorentz representation theory could have a spin 3/2 in it. But by Bianchi identities, spin 3/2 is absent, at least if you impose this constraint. So the non-trivial content of this equation is that a spin 1/2 field W is enough to characterize this curl. Okay, and this is the object that appears in the equation of motion for the vector. Whoops. Okay, now that we have seen the W field on the right-hand side, we also want to make sure that we know the covariant derivative of W. So by starting with this fermionic spinorial field strength, we arrive, after the alpha, at the bosonic field strength, the curl in vector-vector directions. So finally, to make the whole system close, we should also evaluate the covariant derivative of this field strength. And this gives you, so here I'm anti-symmetrizing in a vector index. Okay, it starts to get artistic. Okay. Yeah, so these are the full nonlinear equations of motion that you can pull out of this constraint together with Bianchi identities. And some of you might be rolling their eyes. Ultimately, we are after the string spectrum, which is about the linearized equation of motion. But in tomorrow's or Thursday's lecture, you will see a concrete manifestation of the nonlinearities in the OPEs. So this is something I still recommend you to write down, but in the next blackboards, this will be absent after linearization. Okay, I was occasionally alluding to the parallels with Maxwell Electrodynamics, so I should definitely have an analog to the gauge freedom in Maxwell equation. And the equations of motion you see over there, they have an invariance, under the following nonlinear gauge freedom. So the more obvious part will be what happens to the vector field. Cook up an arbitrary scalar superfield, which may depend on x and theta. And the symmetry, the gauge symmetry of the equations of motion is that you shift the vector field by a nabla gradient with a nonlinear term, and you must at the same time shift the A alpha field by the analogous fermionic nabla. Okay, and the symmetry of the action is such that if you do this operation on the fundamental fields, A alpha and AM, the corresponding field strengths turn out to be covariant. Okay, I already wrote it upstairs, so you can view this just as a definition of what I mean by gauge covariant. Okay, so if you do this gauge transformation to all the four fields, you will find that these equations of motion are preserved.
Does it exist an equivalent thing of vessel gauge?
Oh, yeah, indeed. This is happening in 3 lines from now. It's Harnett-Schneider gauge. Yes. Okay, so I was already giving you the full nonlinear story in anticipation of a later result we will use. But for the immediate purpose of constructing the spectrum of the pure Spinor string, I can restrict the attention to the linearized case. And maybe you wondered about this double line notation for all the fields. I was using the double line to distinguish the full nonlinear fields from the solutions to the linearized equations of motion. So here, these things without any double line, these are the linearized versions, they satisfy equations of motion like the above, but where you drop all the nonlinear terms encircled in green. So that's the definition of these linearized solutions. And about those things, we can say that they have a linearized gauge freedom. That's something we will shortly see at the level of vertex operators. Namely, the linearized version of the gauge freedom is, for the A alpha field, we just look at the d alpha of some scalar omega, and for the linearized gauge transformation of the vector field, we just do the simple space-time derivative of some omega. Okay, so if you now put everything together, the linearized equations of motion plus this gauge redundancy, you can verify or you can count the number of degrees of freedom. How many degrees of freedom are there in the solutions subject to the gauge freedom? It leaves 8 plus 8 on-shell degrees of freedom. It turns out, in order to label all the gauge inequivalent solutions, I need a polarization vector, which is defined up to adding a momentum with a transversality constraint. And you need some spinor, a chiral spinor, that satisfies a massless Dirac equation. Okay, this starts out as a 10-dimensional vector, and the caveats here kill 2 of the components, which is 8. This starts out as a 16-component spinor, but the massless Dirac equation kills 8. And this is precisely what you know from counting the degrees of freedom of the gluon, or a massless gauge boson. And this is, in the fermionic case, this is what you know from counting the physical components of the gluino, the on-shell components. Okay, so to really make sure we can get to lunch, the proof of this claim happens tomorrow. Oops. And also the answer to Igor's question will come tomorrow, whether there's an analog of Estzumino gauge. Right. Thanks a lot. Oh, okay. You mean choose a pair of directions where you switch on a magnetic field? I I don't see any obstruction.